Good morning, everyone. So we're going to do some more programming today, and I'm going to return to a project that we were working on last time, which was these 6 graph algorithms written in differential dataflow. And when we left last time, I think they're in a state where they plausibly worked. Some of them didn't actually run to completion because triangles are bad, but the others seem to run, and I don't recall that we actually verified their output or anything like that, but they ran in plausible amounts of time, typically, but in several cases being slower than, so like PageRank, for example, much slower than high performance PageRank stuff. But some other stuff, so the reachability and single source shortest paths, for example, use this algorithm, bidirectional Dijkstra, that actually goes pretty quick, and that's cool. In fact, it went sufficiently quick that we had a hard time measuring it because it took a little while to load the data up, and then I forget, it was like tens of milliseconds or something like that to do the search, because we didn't actually have our hands on a bunch of good node identifiers spread all over the graph. So what I thought we'd do today is refactor this stuff a little bit. In particular, what I'd like to do is talk you through arrangements, which are a cool part of differential dataflow. It's a way of, although differential dataflow and timely dataflow are streaming platforms, arrangements are a neat way for differential dataflow to maintain state and share state between computations. For example, in just about all these computations, all of them, in fact, I think, we use the graph's edges. And that's important. We need to use edges for various reasons, I guess, because we're looking at a graph. And most of the ways that we use the edges are pretty common. We can't really see how bidirectional Dijkstra is using them, but if we just go and look at like PageRank, for example, we've got our edges come in, they get joined, semi-joined, I guess, with a thing. And this means that their edges are pairs of source and destination. And this is saying group them up by source and use the destination as data. That's what a join does in this context. And in our neighborhood algorithm, they're also going into joins and the connected components algorithm. We're doing a bit of a funny thing, actually. We'll have to talk through this. We're symmetrizing the graph first, so we're making it have edges in both directions. That'll be interesting. And triangles, I don't remember what they do. This algorithm is not the best one to be using. It takes the edges and arranges them 3 different ways. Forward direction, reverse direction, and then as pairs source and destination is the key. All right, so why am I saying all this stuff? What I'm going to try to do is turn each of these methods into, each of these analyses into a method that we can have in our library somewhere. And the method will take arrangements rather than collections of edges. And what this will allow us to do, if we do it right, is write a program that can spend some amount of time loading up the data and arranging it, and then separately call into each of these methods with the prearranged data, and we can separately measure how long it takes to do the data arrangement versus the computation and stuff. And this is nice. This is going to let us tease apart the amount of time it takes to manipulate and massage the data, which someone has to do for sure at some point. But it's the sort of thing that if you're actually running a graph processing system, hopefully you do this once. You don't do this each time for each algorithm from scratch. So arguably a more accurate characterization of how long a system takes to do a thing is how long, starting from properly arranged data, does it take to get the computation done, where the arranging of the data is is something we don't want to cheat on. We want to report that as well, but it's almost a different thing. So let's look at that. Let's start with some easy ones. Well, I wonder if triangles might be a good one to start with, actually, because it shows off the 3 ways that we might want to imagine arranging some edges in our graph. So it does a few other things here. We might have like a lot of ways to arrange data, actually, so we'll have to be a bit careful here. Triangles up here is also going and putting all of the edges in a canonical direction from small identifier to large identifier. Maybe we'll we'll see what we do with triangles here. That's a bit more awkward to manage in this case, though we can do it. Yeah, so what triangles are showing off is that there are approximately 3 ways to arrange our edge data if we want to think about arranging it. Edges are pairs source destination, right? And we can either choose to say we should think of this as a map from pair of source and destination to empty tuple, basically just a set, right? Telling us for each pair source and destination is the edge present. And then 2 other maps that go either from the source to the destination or from the destination to the source. And differential has a few built-in arrangement methods, arrange by self and arrange by key, that look at a record, and if it has a key value structure, arrange by key will, so if it's a pair, arrange by key will say you want the first thing to be your key and the second thing will be your values. Arrange by self says I don't care what type you have, you are now right, you're now just a map from that type to the empty tuple. And great. So we could imagine running a program. Maybe just start sketching this actually right now. So let's save this as harness or something like that. So this is going to be a new program. We're not just going to be doing triangles anymore. And the rough idea is we're going to haul this stuff up into the upper scope here. And let's leave our timer there. Leave our edges. What do we want to do with edges? So we probably want to hide this for the moment. Perhaps hide the distinct as well. So we just want to get the raw edges as have been told to us. And then we want to think about now arranging these things. And you might say, cool, you've arranged them, what do you actually plan to do with them? Because you don't actually know what computation you're going to be doing, and we don't really. What do we do? And the answer is, I'm going to trash this. The answer is that we can return traces from our dataflow method. So we can do, for example, let as self, comma, forward, comma, reverse equal, and we're going to end up returning parts of these arrangements that are useful for, I'll just write them out now actually, as self dot handle. So each of these traces has a handle, which is a way that things that are not streams can look at their contents, can interact with them. And we're just going to return those. We're not just going to return those. We're going to do a few more things too, just to make sure we don't screw things up. We're going to also do as self stream.probe with. What do we call it? We call it probe. All right. So we want to do this for each of our streams. This will make sure that if we need to step our computation forward until such a time as all of our data are properly arranged, we can do that. Remember, this is somewhat tricky to find out if we just walk away from our data flow and say, geez, I hope it's done. We don't really know until we start looking at things like probes. So at this point, probe will now be monitoring all of these arrangements, making sure that, that it reports the amount of progress that they've made, or reports whether we might still see some timestamps coming out of these arrangements, and we're going to make sure to run our computation until it's not the case. So we had previously said while worker.step. We could actually do that again if we wanted to, because we only have one data flow in play at the moment. Trash this. But let's write it a little bit better. So what we normally want to do is, well, what time do we have here? Actually, that's a good question. I guess we're going to have U sizes, and we're loading these all up at 0. I have to say, I apologize. This is probably actually the right thing to write here. idiomatically, because we don't actually have an input to monitor. So we don't have a reasonable notion of time to look at, right? When we introduced our edges, we said, do it all, just go right in. And these records will have timestamp 0 when they come in. That's just how toStream works. But if we had put any other numbers in here, or we should be looking for a place to find timestamps that we should wait for. We don't actually have one at the moment, so. So we can just do this. And in fact, I suppose let's just comment this out. I don't actually want to delete it. These are good things to do generally. And if this were a streaming computation where we had a stream of edges flowing in, these would be crucial, but it's not. All right, so computation is not stable here. Instead, the data are indexed, which is great. Let's trash all of this. We've got this in another file. We're going to end up rewriting a bunch of those things so that they use arrangements instead of what we have here. And let's see. I'm curious if this builds. New field. Oh, sorry, it's not handle. It's apologize. Trace. It is a TraceHandle, but type annotation. Okay, I can't tell what timestamp the probe should have, so let's hide the probe for the moment. We'll need it back when we start doing our computations to make sure that they've progressed, but at the moment, let's not let it hold us up. All right, and it is correctly identifying over here very verbosely that we're not using a lot of the things that we've defined. That's absolutely true. And the gist is going to be, once we have indexed our data here, that we can now start, in principle, we could start running algorithms that are able to consume arrangements as inputs, which will require some editing on our part, because our computations do not do that at the moment. And moreover, our computations don't actually exist as methods we can call. These are just hunks of binary new programs, each of them. Some of them have methods, like PageRank here is a method. And let's think about capturing all of this PageRank code, and let's find a new place for it. I guess here is a new place for it. Where will we save this? Let's maybe put this back in source. We could have a new folder called computations, and we can call it PageRank. And great, now we have a PageRank program, and let's steal all of these. I suspect we're not actually going to need all of these things, but let's try them and see what happens. Yeah, well, harness certainly has a lot of things that we still don't need. Oh, sorry, I haven't actually I haven't added it to the list of things we need to include. So let's do pubmod computations, and let's create a new file that we will save as the mod.rs file in computations. This is a file that essentially puts some structure in place. So we could, for example, pubmod PageRank. And this should bring in PageRank in addition to, yeah, what have we screwed up? All right, so graphs is no longer this foreign namespace. This is just the crate that we are in. So that's good to see. And this harness stuff is going to get really annoying, isn't it? But PageRank, we have toStream and map, which are not used, which is correct. They were only used to massage the edges as we loaded them in. Let's make the function public so it stops complaining about that. And let's try this again. Okay, so the harness is still complaining, and and then reachable is complaining because of consolidate. Let's fix reachable's issues. Is that 7? And maybe we can think of well, let's just keep writing the PageRank stuff for the moment, because I think we're not too far away from having something to point harness at. So this is now the PageRank library file, and it takes as input a bunch of edges like so, and that's great. We will want to change this though. We want to change it to make it something different. So what we want to change it to be is an arrangement type. And an arrangement type is something that exists in differential dataflow. And to be honest, I'm just going to go and steal the signature so that we don't have to guess about it. Differential dataflow has a lot of very handy things in it. One of the things it has in it is a bunch of experimental stuff that we wrote at various points. And one of them is a bunch of static graph computations, where we go, for example, and create arrangements here. And we then use them. I wonder, oh, I might not even have left the type behind. That'd be embarrassing if just wrote all the stuff in place. No. Here we go. So a TraceHandle, which is a trace agent for a graph trace, which I guess we've decided is going to be that. Great. Let me steal some of these things. We'll put them in our lib so that we don't have to constantly sniff around for these things. Okay. Go away. I closed our lib already. Probably did, didn't I? So we're going to need that. I'll explain what each of these things are in just a moment. We're going to need to change them a little bit too. So that was all. This is all in the context of a one-off graph computation, and it is for a restricted set that don't need to do too many things. So let's talk through what each of these things are here. So first off, two of these things are types, and two of them are using statements. So the use statements just bring in some types from elsewhere. In this case, this is differential dataflow's way of representing internal data mumble stuff. Actually, you really don't have to know what this is. It's cool stuff, but all that we're really saying when we write this down is that differential dataflow wants us to be fairly specific about how we arrange data, and it's not very easy, unfortunately, to say, oh, I don't care, just use the default. We could say that, but we have to announce what that type is. So, right. So what we're doing here is describing a data structure where we have a key, a value, a timestamp, and a difference type, and then some other crud in here that is fairly formulaic but needs to be written down, unfortunately. And with that in hand, we can then describe a trace agent, which is the a thing that we hand around at this point that might be handed as input to a dataflow computation. And we might not actually even use the trace handle. Let's check and see how it's used. The trace handle, or trace agent rather, is a thing you hold on to outside of dataflow graphs, and we're going to be using such a type, but we'll probably be handing around as arguments the graph trace. That is, when we call PageRank, we're not going to ask PageRank to build us a new dataflow. I suppose we could, but we'll probably instead have a dataflow built already and hand it the arrangements and say, go to work. Build just the nodes in the dataflow, don't build the dataflow itself. So let's look and see how these things get used when we do these sorts of things. So the way this is our static graph. This is where we were using those trace handles and stuff to do graph reachability. And the code as written here says, give me a trace handle, give me some collection of data to start my reachability queries from. Yeah, and then it handles importing the graph into the scope. We might want to do that ourselves. It's something that this method doesn't really need to know about, and it's also a bit problematic if we wanted to. It restricts how we can use this method. So if this can only be handed a thing outside of a data flow, that's annoying, because if we're already in a data flow, what are you going to do? Whereas the other direction, like if this took something that is already arranged and in a data flow, well, if we're not there yet, we could call import in whatever our data flow is, and then just hand the imported thing off to this method. So we're going to try that. We're going to try writing something that probably takes a graph trace as an argument. We need to change this time, though, because this is not right. Or at least in several of our computations, we're going to actually do multiple rounds of computation because we have multiple, for example, multiple search points potentially for graph reachability. We could ditch that. Like we could say, no, each time you want to do a graph reachability computation, it's a new data flow. You got to start from scratch. I wonder. That's not nearly as fun as, but we are doing static graph computation, so maybe let's leave it like this. A good thing that should happen, I believe, is that our starting from scratch logic will still be surprisingly fast, because that's one of the cool things that arrangement does for us, is it removes all this overhead of arranging the data, and we only have to pay for building the data flow graph and then running the computation. Hopefully we'll see that that's really fast. I hope that it is fast. We will see. All right, so let me leave this just how it is. This is nice because this type has no generic arguments in it, right? Which is handy, because that means if when we compile these methods, we are not going to we're not going to necessarily need to do lots of recompilation on the library. Gets compiled once, and the binaries, even though as we change them, we won't necessarily have to do massive amounts of recompilation. So I think we won't need this. So let me just comment this out for a moment. And when back here, we're going to think about edges being a graph trace, right? Which is something that we will have had to have brought in up here. Graph trace. And what do we do with our graph trace now? Well, let's look. So we need to, we do use it quite a bit, right? So we're getting our degrees out. That's something we can definitely pull out of here. So we're going to potentially do a little bit of work, even though the data are arranged for us, flattening the data back down, right? So for example, we need to figure out what are the set of nodes in the graph. We need to figure out what are the degrees of the edges in the graph. And to be honest, these are things that I'm pretty sure we're going to end up going and computing once. So we'll end up with like a nodes arrangement also. And in fact, let's prep that right now, just because I don't want to have to write the wrong thing and then fix it too many times. So let's let this be an edge trace. Right. And at the same time, we're also going to put together a node trace, which will be is going to look like this is a different way of storing stuff internally. It says if your value type is the empty tuple, don't bother telling me about it. I will optimize its representation and give you a better experience. We could totally have done this with the previous, just replace this type by an empty tuple, this type by an empty tuple. And all that would happen is that internally we'd have a bunch of arrays that contained all the possible different values we might have. We know that there's exactly one, no more, no fewer. So there's sort of no point in actually writing it down and having a bunch of allocations just to hold those things. So great. So we've got this in our mind. Let's think about adding that as well. Okay, so we've got nodes and edges. We don't need to do this. Well, hopefully we don't need to do that. We'll see. We still need to figure out the degrees. Maybe we could pre-compute the degrees too. It turns out a few people do care about degrees, not just PageRank. But for the moment, let's not do that. Let's instead drop this down here and just format things a bit differently. So Trace has a method called as collection, which takes as an argument a generic anonymous function, a lambda, from pairs of keys and values. Sorry, not from pairs of keys and values, because they're not represented as pairs in memory, as a two-argument anonymous function of key and value. And we can actually see from the next line down that we don't actually want the destination, we just want the key. So we'll give these better names because we know what these are, source, comma, dest. And we know that we don't really want the dest, so we don't need it. So what's going on here is that inside the arrangement, we have all this data, but we don't get to take ownership of it. These are just references. So we need to explain, the as collection says, show me all of the show me all the data, basically. Show me all of the sources and destination pairs, and I'll tell you what to do with them. And we're quite happily saying, great, if it's a reference to a, actually let's fix this just so that if someone were to change the node type on us, we don't necessarily want this exploding. We haven't written perfectly generic code all the way through yet. But. All right. We now have an iterative subcomputation, which is great. Many of these things are going to work out exactly as advertised, which is sort of neat. In the sense that edges also has an enter method, even though it's an arrangement. It has an enter method. Nodes has an enter method. Degrees has an enter method. Nodes, this is going to be not super helpful, is it? What we want to do here. Now, the arrangement does not have an explode method, so we'll need to again call as collection on nodes. But here we can actually be a bit more explicit and say we happen to know the type, and we're going to ignore it. This is potentially minorly inefficient initially in that we're scanning nodes twice. We could sort of scan it once and then fork the stream, but let's not worry too hard about that. All right. So we've got some computation here using degrees, using ranks. I don't think we can improve this at all. Maybe yes, but maybe no. The thing we're really looking to fix though is over here. Edges dot semi-join. What's going on with that? So we're going to replace the semi-join. We're going to replace it because we have to. Or do we have to? Fascinating. Actually, I don't think we. I'm sorry. I take that back entirely. I believe there are methods written for arrangements that have semi-join already defined. So this plausibly will just work. Do you believe that? I wouldn't believe that. Let's see what happens if we. Go check this. we've got some errors. We've got some other types that we need to use. Great. I'm gonna find type RC. Cannot find spine. So okay, so this is just twice the same errors. No. Okay, wrong number of type arguments. Expected 5, found 4. That's correct. I totally forgot that although the order to keep batch does not need a value type argument, the spine doesn't know that. The spine needs to know, like, what are you pretending to present as? And 4 errors. Oh, great. Okay. So now we're off to fixing errors in PageRank, which is great because this is where the errors probably are. No method as collection, 28. All right, so we have the same issue here as we had. Oh, no. No method as collection. Have I screwed that up? Let's, we know where that should be. Oh, I'm sorry. I lied a little bit. Or I lied. I was just wrong. We probably will need this, or something like it, which is following. Edge arrangement equals, and we'll figure out what it is. So that trace is actually, all that we described with edge trace and node trace was the internal data structure. We didn't describe the thing that we're actually going to be handing around. So let's go find out what that is. Differential data flow. I believe it's going to be just an arrangement. But let's check. Where are we? Source operators arrange. Arrangement is probably one. Though actually, let's check here. I think this is where we have a trace agent, and we can look and see what the type for import would be. Trace agent has a lot of methods. Import returns an arranged of G, trace agent of the trace type. So that's good to know. What this means is that we will want to write a thing which is essentially, is it just arrange, is that right? I can never keep straight the arranged, okay. Arranged, G, trace agent, edge trace. And this will So you would be right to complain that this is not sufficiently ergonomic yet. Not to worry. Or, I mean, you're correct. Let's see, we might need also arranged. Where does arranged come from? It's just in instead operators of arrange, I believe. See how this looks. Oh, well, sorry. We can see how that looks, but we'll need to tidy up the PageRank stuff before we actually expect anything to happen. So, we'll call it an arrangement. This is absolutely the sort of thing that wants to live behind some nice type defs somewhere. Okay, hold on. Oh yes, we need to give it a type argument, which is G, the data flow graph in which it exists. Still got errors. Oh, thingy. Okay. This is almost certainly going to be fine. I just need to get my head around what in the world's actually going on here. So this is complaining that the method certainly exists, so you can find it, but we have failed to convince it that we're authorized to call it. Why is that? Let's look at it. So a standard reason this happens is because there's some incompatibility between the batch type here and the thing that we are pretending to be. Let's see if this so it looks like both of ours, I'm just looking at both edges and nodes are screwed up. Why would this be? Let's take a quick peek at a few things. So there's a few standard things to double check anytime you get told you're not implementing a thing. One of them is you want to make sure that you're using the right versions and that everyone is talking about the right version, because if that's not the case, Rust just silently tells you doesn't implement things. That does not seem like that was the problem, though. So new method as collection found for all that crud. Let's go take a peek at these methods. See if we can sort out what's missing from the where does as collection live? So we need to track down the arranged type, which is in arrangement. It's over here. For some reason, we can't find this method. Oh, sorry. Yes, because it has generic arguments. So for this to work, a few assumptions need to hold. Our timestamp needs to be lattice and ORed. TR needs to implement trace reader. This is telling us something over here, but I can't for the life of me. God, barf. All right, the problem is, good, I see it now. The problem is we've committed to a timestamp here, but we have claimed that this is going to work for general G with arbitrary timestamps, which it can't do because we're only able to, let's get this out of the way. We're only able to work with certain class of timestamps, G where we won't need this anymore. So I think this is approximately the bug. I hope I haven't written this sort of stuff in a while. That doesn't look right. For some reason, my brain is spacing on the right way to supply constraints for these things. Let's see what happens then. Oops. get to do this. This is the downside of calling cargo update and stuff. Some creates update quite a lot. That's what we wanted to write. Sorry. Yeah. So it's trying to understand what the hell is going on with our weird syntax there, and all we really wanted to say was this. Not sure what my brain is doing. No method scope. Okay, that makes total sense. There is absolutely not a scope. Well, there could have been a scope method, but instead we're just going to grab the stream component of the arrangement. What's this other thing here? No field inner on type reference to a thing. Oh, it's probably just because I can't figure out. Yeah. Cool. All right. So now we have a. I got a method. PageRank. Let me clean up some crud here. Got a method PageRank. It takes as input a number of iterations, which turns out if that's 0, it does unboundedly many. Maybe we should make that be an option. So it takes in an arrangement of nodes meant to be distinct node identifiers, takes in a bunch of edges. Super handy. We will go and do iterative computation. We'll have to do a little bit of work because this degree computation is non-zero effort. But otherwise, we just get going right away. So if for whatever reason, I mean, this is sort of a fun thing you can do now, actually, which is that we've decoupled the graph edges from the reset distribution, from the place that we distribute probability mass. So you could show up with, you could do, I don't call it personalized PageRank, but you could show up with a bunch of weight, basically, in the nodes, which it is going to go and explode out by these amounts here. So if you want to do something other than uniform over pages, you could totally do that, and you could interactively update it. If we had not committed to having a BOGO timestamp here of no time, you could interactively update nodes, and that would modulate your PageRanks as if you had changed the reset distribution, except to be doing it incrementally rather than from scratch. Fascinating. All right, so this builds. Let's think about changing our PageRank algorithm, our PageRank, sorry, binary, to handle this for us. So so we can ditch in principle all of this stuff. So we've still got our edges, they're still coming in, they're still getting turned into collections. What is this? This code is crap. Wait, hold on. In our PageRank thing, we were symmetrizing, or not symmetrizing, sorry, we were undirecting the graph, which is totally wrong. You don't want to do that. I mean, you could do that, but like it's just wrong. It's a different graph. So we're not going to do that. We're going to do as collection, and we're going to do arrange by key. Awesome. And let's also get some nodes. So we're going to need to do as collection here also. For our nodes, but we're just going to, what's the right thing to do here? Let's just do source. So there's a question, legit question of like, if you have edges that point at nodes that have no outgoing edges themselves, do they get reset probability or not? And opinions vary. One problem being that there's a lot of pages out there that have incoming edges but no outgoing edges, only because you haven't gotten around to crawling them yet. And if you give them lots of probability mass, then it just drags it away from everyone else. So this isn't a super exciting thing to do. Let's do distinct and then arrange by self. If you're a clever person who's been paying attention, you might also know that distinct itself actually produces an arrangement. So this is totally redundant. We really don't need to be doing this. We could totally crack distinct open and borrow its arrangement. No, we're not going to. What we're going to do instead is graphs, computations, PageRank. And what did we take first? Nodes or edges? Nodes first, then edges. All right, this might work, or this might build. Let's check. No, we have to ask for arrangements. This might actually be the same thing to put as an inherent method on collections, because arrangements are pretty fundamental. So, what have we screwed up here? Expected a blah, found an integer. Okay, so when we imported our stuff at time 0, what we should have imported it at was time nothing. That makes sense. We'll have to grab arrange by self also. Alright. So, two things, right? So we don't use dest in here, that's absolutely correct. And also we don't use the PageRank method anymore. So we can just delete that. Awesome. And we haven't really cost ourselves too much, I don't think. So this edge arrangement, we're going to have to do anyhow. This happens as part of the semi-join, unless we've already done it, in which case it doesn't happen. The nodes arrangement had to be done at some point, so glad that we did that. And, you know, arguably, degrees is probably pretty pleasant, actually, because edges is going to be already arranged by source, and so when we turn it into a bunch of source things, again, one for each destination, okay, that's annoying, but this is going to be nicely, you know, all of the sources will be right together, all of our, what do I want to say? There's going to be lots of friendly memory locality and lots of compaction that happens because the data are already pretty much arranged. If we had multiple workers involved, there might be some data exchange, but nothing would actually hit the wire because the data are already shuffled by source. So that's great. Let's just double check this. Did I not save? I just did delete it. Why did I fuck up here? Could have sworn I deleted this. All right. Oh, cool. And now that we've deleted it, we can also tidy up like a whole bunch of this crud up here. All of these things go away. Product and collection go away. Also get variable, join, count, and filter. Variable, join, count, and filter. That's helpful. Yeah. All right. So we've got a smaller program now. One that, I mean, it's smaller in a sense because we took the logic and put it somewhere else. But we're now relying on some PageRank computation that we, yeah, it's all good. So, yeah, let's see. So PageRank is all set. In principle, we could add PageRank to our harness that we're writing. And we can see what that looks like. So, oops, we don't want to leave that there. So what does this look like? we build a new data flow. Okay, so we've loaded our data. We have these 3 arrangements on hand. Maybe we want to do nodes as well. That seems not unreasonable. Let me blot this down. So let's also put in, for example, nodes. We could do these one at a time on separate data flows, which would allow us to see for each of them how long do they take. It's not unreasonable. But let's suppose we should hold off on saying that until we get down here in case we ever wanted to probe results. I'm going to put a little to do here that we should almost certainly look into. Looking into getting the arrangement out of the distinct. Because we're doing redundant work there, that's at the moment it'll just be attributed to how long does it take to load and index our data. But yeah, so if we're going to do PageRank, we would want to do something like graphs, computations, yeah, good. PageRank. PageRank is both the name of the method and the name of the module. But, all right, I'm typing some stuff which isn't right yet. We need to import these nodes and forward things. So let nodes equal nodes.import scope, and let edges, it's not the right name, but equals forward dot. Now what's going on here is that at this point in the code, these 4 arrangement or trace thingies are just data. They're not. They have no hooks into timely data flow. They're not. We're not tracking any state about them. They are essentially a queue that is continually producing batches of data and a little bit of information about progress, which is absolutely timely data flow concepts, but they're not. This scope doesn't know anything about them. So we need to bring them into play in the scope by saying, could you put together a data flow operator for me that has no inputs and 1 output, and don't worry, I'll drive that operator around. That's what this method is doing. And now nodes and edges are things that we can use to do PageRank sorts of computation. And I'm just going to steal the printing. Really? Triangles? Who wrote that? Yeah, screw it. We're not even just going to look at the output. I'm not sure what output we would look at for PageRank, so we're just not going to. Ta-da! Oops. Ta-da! Yeah. So, this now has done PageRank for us. PageRank computed. So let's cargo check in harness. No method distinct found for, yeah, that's true because we did not dereference source because it's a reference. We just said, oh yeah, make a collection of references, and differential said that is not acceptable. So again, we need to make this be so. Expected close. Oh, did I not close a? Thought I closed it. It's closed to me. What are you talking about? 72 is not closed. 30. Oh, did we screw this up somehow? This one is not closed, it says. Oh, it's horrible, horrible. Sublime is, or I guess this is, sorry, not Sublime's fault, but though Sublime does the same thing. If you just type open close paren in order, you get not what you wanted. Great. So we need to make these things be mutable, because when we import them into data flows, we are changing them. So internally, they're keeping a list of who do I need to tell about stuff, right? All that we're really doing now is going to cause a whole bunch of you shouldn't have made this mutable warnings, but yeah. So when they get imported, they change. The data don't change, but the handle, which needs to keep track of who it needs to tell about things, changes. Cool. All right. What's a good next one to do? Some of these are going to be interesting. Let me talk you through the ways in which they might be interesting. Tidy a few things up here. I want to keep this open because this is important. But PageRank we can shut down for now. So like neighborhood is going to be super pleasant, I think. We could do that one next. Connected is going to be a bit interesting because it goes and symmetrizes the graph. And that's fine, actually. It turns out that there's a neat transformation we can do that allows us to, instead of symmetrizing the graph, use both the forward and reverse arrangements to cause the same thing to happen, basically. Though we'll have to rewrite some stuff. That's absolutely the case. Reachable and SSSP are going to be a bit awkward because the Dijkstra algorithm does not take arrangements in its input. And what I thought we might do when we get to here is fix Dijkstra to do that, because it can. It's totally possible for it to take arrangements as input. I'm a little worried that we've been fairly specific about what type of arrangement should we take, and if we're going to write something that's super general, it might end up being a bit grotty. But we could look into that and see how that works. So both reachable and SSSP will be simple if we can fix Dijkstra, bidirectional Dijkstra, to take forward and reverse arrangements, which are the two things it needs. And then triangles, or triangles. Oh, we close triangles because that's our harness. There we go. Got triangles again. Triangles should be pretty easy because we just need to hand in as self, forward, and reverse. Though we will want to filter them, which in principle is fine because traces have a filter method. But let's see. You might notice over here we also have a degree counting thing going on. Yeah, let's see. Triangles will certainly be easier if we were looking for directed triangles rather than undirected triangles. And that's the main reason that we're doing this filtering, is to look for undirected triangles that symmetrize the graph, filter it down to be small to large, blah, 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 blah. I've been told we're actually looking for directed triangles in the graph as like a problem statement, but it's not entirely clear what a directed triangle is. I mean, there's lots of things that a directed triangle could be. But let's take neighborhoods first, and let's port this over. So we are going to create a new file. We are going to blot this down. We're going to save it as a computation. Neighborhoods. Great. We could speculate on what methods or what types we're going to need here. Speculatively, it'll look like this. Sure, just copied that, I guess. We will need to take edges not as a collection, but rather, however PageRank took it, which I think was a edge arrangement of T. We'll leave the source just as a collection. These are the goals, basically. No, not the goals. Sorry. These are the points from which we do the outward reaching. This is probably a really small collection. We're probably not going to reuse it in a lot of places. So we've got our computation. We do all of this, and then a join map. Now, we could try to leave join map in there if we wanted. We'd have to change the order that we do the joining on, because while arrangements can have a join map method, collections cannot have a join map method that takes two different types of our first argument. So join map always has to take the same type for its first argument. That type is a collection. What we can do instead, if we want, is use the join core method, whose first argument is an arrangement, and is sort of the internal most programmable piece of a join operator that we have. So we write that some more node. We don't want node. We don't care. And it needs to produce an into iterator as its output, because it is very programmable. But that's possibly sufficient. We might need to go and change this to join core. Let's see if I've gotten ahead of everything there. Alright, what did I screw up? Oh yeah, this is not greps anymore, this is just crate. Looks good, right? Oh no, no method enter found for arranged. This is probably, again, this nonsense here about how the timestamp should be exactly the empty tuple, no more no less. Looks good. All right, so we now have a neighborhoods method. We could change our neighborhoods now to, just like before, load these things up as collection dot arrange by self, and then we could do edges. I think we want a reference, probably. How did we define it here? I just said take the whole thing. We're gonna want a reference here. And we have a bunch of visualization things that we want to do. Let's presume that this will be irrelevant. We will need to add arrange by self, I think. Let's let Rust tell us that, because that way I don't have to find the whole path. Arrange by self. What do we need now? Oh yeah, no, that's just totally wrong. Still some error. Neighborhoods with 2 S's. Okay, great. Expected type integer. Oh, this is just. Don't fall for that thing again. All right, so our program is written now. Wanted to we're not going to spend a lot of effort on this particular thing. Wanted to separately track the amount of time to do reachability stuff. We're not going to do that anymore. We're just going to sources dot. Oh, this is a little too bad. I feel kind of bad breaking this slightly cool example. But, oh well. Function neighborhoods is private. Did I? Yeah, okay. That's good. Right. So we've broken our example, and we can't do multiple neighborhood readouts in the same data flow. That's too bad. I guess the old version will still be in the Git repo though, so in case anyone wants to check out what the world would have looked like back when we did those sorts of things, they can. So our next step is to fold this into harness here. So we're going to take another bit of data flow here. Where we will take this code. We need to figure out where to have gotten our source from. So yeah, all these things that take command line arguments are going to be annoying, aren't they? So we can let the source be, what was our philosophy up here? So someone's giving us a file name for sure. They have to point us at some edges. I suppose we could pick these out. We could write a more complicated, like little interactive, what data flow should I run next, and with which arguments widget. I think I might leave that as homework for other people. So source is going to be, let's see, who remembers in which order we supplied these? When we insert them, source and then steps. Okay. All right, it takes a reference. This does not take a reference. That's fine because we don't need it for anything else. Yeah, it might plausibly work. Let's always inspect things. Iter. Did we not bring in iter yet? Now we have. Progress. Cannot for an appropriate lifetime due to conflicting requirements. Where are we? 75. And why is this so hard? have no idea. But I'm inclined to think that we want to put this inside the dataflow thing. I'm a little worried, possibly, that it's having a hard time figuring out if it should borrow or move. No, okay, still an error. Boy, why scope, import scope. Cannot infer an appropriate lifetime due to conflicting requirements. So the lifetime of scope cannot outlive, scope. We don't want it to. Oh, good. So this is Rust's passive-aggressive way to say, hey, watch this. You should have put a semicolon. Thanks, Rust. So what was actually going on there, right, is the return type of dataflow. So this was resulting in a value without the semicolon, without a value, so it should return it. And there are some lifetimes associated with scope baked into this bit of thing, and indeed we absolutely do not want to return the differential dataflow collection that results from inspect, that code right there. All that we really needed to do was put a semicolon on the end. Neat. All right. So that's neighborhoods computed. Let's tidy up some more things. Come on, let's behave ourselves. So let's get neighborhoods cleaned up. What we might do now is do the graph connectivity thing. The problem with graph connectivity is we have to pick open the label propagation algorithm. We had cleverly just said propagate at before. And propagate at doesn't understand arrangements. Now, we could make it understand arrangements, but we don't actually have an arrangement that is the undirected form of the graph. So we would have to get one of those. What we can do instead, and what we did in our nice little program over here, the one that we used while evaluating differential data flow, was the following. It's got a bunch of crazy stuff in it. Don't get too stressed out. Was to say, if we're doing our label circulation, we could totally go and propagate those labels along the forward edges, propagate the labels along the reverse edges, and then concatenate the results together. And each of those propagations, forward and reverse propagations, is just a join with the labels. And so that's fine. And we can use now arranged forward and reverse edges, which is great. So we can actually try to steal this. Let's see if this works. Apparently there's an odd version of it as well. If you didn't think this was odd enough, there's an odd version of it. But we can go and put this in a new, so I don't want to save it just yet. Now, there's a fair bit of complexity in here just because I'm screwing around trying to make things go fast. We have things which are eventually going to be called edge arrangements. Forward and reverse edge arrangements. And we don't need to import them anymore because the edge arrangements are the imported versions of them. We can also take as input our nodes. So this is part of the computation that's going and trying to figure out what label should we start from. If you recall, the connected components algorithm starts all nodes with a label, which is their own name, basically, and repeatedly circulates that label along all the edges where every node retains the smallest label it's ever heard of. And in the fullness of time, that means that the labels identify the connected components, because the smallest label in any connected component will eventually take over the whole component. So this was trying to make the initial label determination from the set of edges as fast as possible, because that is surprisingly expensive. If you just took all the edges and said source, dest, each of those need a label, do a distinct. That's really expensive because you're doing essentially a full edge shuffle at this point. Every single edge contributes a bunch of stuff. So what we tried to do here, which was clever, is say, well, for the forward edges, let's use the source of that edge, because the data are already shuffled that way. That's great. And for the reverse edges, we'll use you to pick out the other input. Basically, those are indexed by dest rather than by source. So we'll have you propose the dests. In both cases, these are the keys. And it turns out you only need to propose the smaller of the two, because for any edge source dest, obviously the smaller of source and dest are going to immediately dominate the larger. Okay, but we don't need to do any of this. We can just do hilarious. Node arrangement. That's very interesting. So, my mouse. So we've got some nodes, some forward, some reverse. Apparently, we're defining a variable. This is stuff. This is all, strictly optional. We're trying to be clever and realize that something. I'm not even sure. Let's see if it builds. It won't build. Let's see what we need to do to get it to build. Probably it's going to be importing a whole lot of these sorts of things. So I'm just going to start by taking all of these. And let's take, where's my, do we not need to know about nodes and edges here? Let's do some more important stuff here. Define type product. So it might be worth thinking out, do we really need to do something that's quite as complicated as this variable thing? I'm not entirely sure why I've made it so complicated. Let's not screw with it. Just do what Rust tells us. Scope. So we'll get product in just a moment. I just want to type some other things first. Yeah, I really want to paste that into the console. Variable is imported redundantly. Wow. 8 and 26. I don't see M26. What is this thing talking about? Oh, I see. Yeah, it's not 26. I was 20. All right, what do we got? Node is not known to us. Diff is not known. So let's fix those. Node diff still 2 errors. Still doesn't know about product, and what's the other one? No field inner. Oh, because it doesn't know about product yet. So this is just a timestamp combinator that Timely provides, and which is used in iterative computations. So if you want to set up your own iterative computation, you need to talk about this type. No field inner. Do we still have? Nodes, yes. Nodes does not have an inner. That's a good point, because it is an arrangement. So instead what it has is an as collection see how that, then it has an inner, actually. So this is, I shouldn't have to have shown you this, sorry, this is gross timely data flow screwing around idness, where we are delaying label propagation by size of node. Why? What a mess. Well, I guess, sorry, this is us trying to be responsible and say we don't know how big your node identifier is. And since we're going to use there, it has some number of bits in it, and we we're essentially taking a logarithm there. That's what's going on. Sweet. All right, new errors. Expected U32 found a tuple. Fascinating. U32 doesn't have fields. That's also true. Do we? Oh, maybe we expect nodes to have come in. Let's check with as labels already. In which case, where's connected components? Yeah, nodes is already pairs of things, so we need to make it look like pairs of things. So we're going to bring into the scope, and we'll do as collection. Now we can totally just ditch that. We don't need to do that anymore. So nodes is now just a collection. We weren't actually, we're not using it in a join or anything like that, so the arrangement doesn't really help us except for avoiding the massive amount of computation we've had to have done. Cool. So that looks legit. I'm pretty okay with this now. And we can add it to our harness. Maybe. What did we inspect here? Goals, ridiculous. So what we could produce is like the component sizes, for example. That seems like a totally tasteful thing to propose. I suppose what I have to do though is steal some more of this stuff. So components, do they take in? Oh no, they don't take in nodes and edges. They take forward and reverse. Forward. Takes a scope. Why does it take a scope? That's silly. Let's not have it take a scope. We can just take I assumed before it just had trace thingies coming in, so it didn't know where to build them, but now it's all good. Right. Could not find components. Did I call it something? Oh, connected. Probably. Almost certainly connected. Cannot find function connected. Pubmod connected. Connected has a connected components method. Let's just call it connected. But it does need to be pub. Oh. All right. So these things, it wants them to take mute arrangements. We don't actually need that. Back when they were handles, they were mutable so that we could modify the handle. But now that they are arrangements, doesn't matter. The arrangements have some interior mutability stuff going on, which more or less means that they end up cloning themselves. But it's all good. Unused variable inspect in harness, line 19. Oh yeah, we are. Let's not put inspect here, because I don't think we're ever using it, as Rust has told us. And let's go and actually do something here with this stuff. So these are the connected component identifiers. We can go and grab the labels. And then count them. And then take the counts. And look at the counts. No, count them again. That's fine. I mean, we don't have to count them again, but we could. So this is just going to tell us how many components are there of each size. So that would be just a println. We're going to do this with boom. Let's do 2 tabs just so we have our semicolon, very important. Don't forget your semicolons. Okay, we're gonna screw up some other things apparently. Yeah, our map closure, these things are pairs, they're not. So the map closure takes one argument only, the record. If the record happens to be a pair, you take a pair as an argument, you do not take 2 arguments. Timer doesn't live long enough. Oh. This is super annoying because I don't want to have to move the I guess what we do is this. If you can type move here, and that will move the type array which clones it, but I don't want to move these arrangements in. should be able to do it, I think. Why is that not a problem up here? Oh, is this just a problem? Maybe this is all fine actually. Let me not do that. Yeah, okay, cool. Apparently I'm putting the timer somewhere else. Nice. Apparently not necessary. Very cool. So yeah, let me try ooh. Try a release build of this. Which we can then run maybe on a small graph and just watch it tell us various interesting things. It'll take a little while because it is linking in complicated algorithms. Unfortunately, this is possibly an anti-feature, but unfortunately all of these differential and timely data flow things that we write get connected. No, not this one. This one's fine. So things like connected here are generic with respect to G. And G isn't actually a very interesting type, but it has a lifetime in it. And one consequence of that is that we do a bunch of code gen because Rust doesn't know a priori. It could be lots of different types there. We could be more specific and just have the lifetime as the only generic parameter. I don't know if that will prevent monomorphization or not, which is what's causing all the compilation to be slow. In principle, people can have different implementations of things for different lifetimes, which means that we would need to recompile for each different scope, even though we'd like to figure out some way to promise, please, this isn't interesting. This is a different type only so that we can yell at you if you get it wrong, because we don't want you mixing up streams from different scopes. This decision was made 4 years ago, and could possibly be revisited if it's very painful. But let's see, we're compiling this stuff. We've got connected components there. We have these 2 reachability and SSP things that we would want to change bidirectional extra for. We have our triangle computation, which I think, with the exception of the fact that we need to filter things and, to be honest, probably have made them symmetric in the first place, we can do this annoying thing that we did before. I don't really want to do this, but the annoying thing we did with connected components, which was to say anytime you actually want to use forward, you should join both with forward and reverse, and then do a filtering that does keeps the right subset of edges there. So we can put together the forward and reverse edges for you, and then let you use some algebra essentially to distribute any joins you want across the forward and reverse relations, and then filter down to the things you actually want it to keep. Maybe the better thing to do is just to, if we cared, maintain the graph and also the undirected form of the graph in our harness. So where we're saying like, oh yeah, we're going to keep self, forward, and reverse. We added to that nodes. We could also add some undirected representations of things that make life not too hard for people who want to flip-flop around between directed and undirected representations. I'm not urgently interested in that. I mean, it's the same thing to think about how do we want to do this, and it's very reasonable if you're building a graph processing system to think about which representations do we make cheaply available to people, and is there a clever way to do both of them at the same time. Great. So let's see what this looks like when we run this. Oops. So we need to go and find a what do we have in here? So I've been using LiveJournal raw for a little while. What's like a tiny one is probably, well, Miko is tiny. And we give it node 0 with 3 steps. So that's the sort of thing that we see. And we just did our, fascinating. Did we actually report the components were done before they were actually done? Yeah, okay, we're not even doing the worker.step thing. This is a really important thing to put in your code, everyone. All right, now we get to test the incremental compilation functionality here. I think it took about 3 minutes before, though I have forgotten now. But we can just sort of look at some of the data if we want to see. Apparently, I have no idea what neighbors is actually reporting. It looks like what in the world is going on? I've got no idea what this number means. What does neighborhood produce? It probably produces all of the nodes, right? And maybe the distances? So probably what this is saying is that there is one neighbor. Ah, that can't be right. That shouldn't be the hard part. Let's while I was building this, I'm going to refresh my memory on So neighborhoods produces a collection of node and node where it's a source and a destination. So pretty sure, right? Yeah. So this is the query node and the places we were able to reach, ignoring the number of steps it took, distincted. So when we take that and say who can do the reaching, it looks like, I think I got this backwards actually. I think I asked from node 3 with 0 steps. Let's try to confirm that. Yeah, steps and then source. Okay, so this is just me being dumb. In 0 steps, 3 can reach itself and no one else. About a million edges, it's not very many. Maybe we'll point it at LiveJournal in just a moment. You can see this took some time here, and then almost no time to build the data flows and then not actually run them. So PageRank is what took most of the time, looks like. It took a little time to load the data, a bunch of time to do PageRank. Let me fix the neighbors thing. So we were able to find 237 neighbors this time. Quite promptly, right? In 2 milliseconds or so. And that's 2 milliseconds to build the data flow graph and run it to completion. So let's take a slightly bigger one here. Oh, So LiveJournal took about 3 minutes to do PageRank on. I'm not sure I really want to sit through all of that. We got, how small was Miko? Miko was 4 megs, so if we go up a little bit from 4 megs, wow, these are even smaller. It's amazing. Yeah, I think most of these are just bigger. So the next best thing maybe actually is LiveJournal. We do LiveJournal.targets, or LiveJournal, sorry, without the raw. Let's just do it with the raw. All right, this will take some time. Some of the times could be doing arranging, which is great. I mean, great in the sense that, hey, there we go. Okay, so that's 30 seconds to produce the forward, backwards, and by self arrangements. And the good news is that for many of our computations, we're actually using those, so we don't have to do them a second time. This is, if everyone had used all 4 arrangements, I guess, with nodes, this would be 30 seconds that everyone would have to do. Now, not everyone uses all the arrangements. We could have built them lazily. Or we could have ordered our computations so that we do the people who just need forward first, and once we need reverse, then we do reverse. But yeah, PageRank will take a little bit of time because this is the one that took. Well, first of all, it had a bug in it, right? Because we were throwing away, we were undirecting all the edges, which I have no idea if that is good or bad or what that does. But it might be different. Yeah, PageRank is slow and crappy. Another thing I was tempted to do as part of this video was to take the cost computation for PageRank and change it so that the node state is held in a hash map instead of a vector. And you'll see then that differential's time is not nearly as embarrassing as it was. I think it was 10x slower maybe than, we looked at it in the last video, maybe 10x slower than the cost version. If you force the cost version, the single-threaded version, to use a hash map instead of an array, it gets a lot slower. The data locality goes away, there's a lot more math to figure out where you should go and drop the data that you've computed, and it's just a bit slower. And what that means is that algorithms that go fast with array implementations for state are kind of relying on the fact that someone has actually gone through ahead of time and turned all of the node identifiers into dense integers, which is fine. That's a thing you can do, but if you're not telling anyone that you're doing that, that's a bit of a problem. And most people don't bother because the data that they get, this has already happened. But if you took their code and went to a real environment where the usernames are strings or something like that, web URLs, someone's going to have to go and do that step. You could hash things, for example, possibly legit, but you still have now sparse identifiers, probably like 256 bits wide to avoid collisions. And you can't use arrays for those either. So it's an interesting point of comparison to make. if you're not in the business of pre-processing your graph, because you got real data, the real data changes, you can't just freeze it for the next month and aggressively pre-process it. What different trade-offs would you make now? Are we really quite as impressed with the land speed records of the single-threaded implementations, or the graph processing systems that make those aggressive pre-processing steps part of their, I would say part of their workflow, except again, usually they're not reported. So. Let's take a peek at Activity Monitor just to check that we're not accidentally blowing anything up. Yeah, not really. It's just slow. PageRanks have been computed. Quite a while, actually. I forget if it was, for some reason I thought it was 180 seconds. Last time, that might be making that up, but this is twice as slow. Neighborhoods we found was 100,000 neighbors in, where'd it go, 140 milliseconds. Not so bad. And then in an additional, I guess, 34 seconds, we found all of the connected components. Good for us. And, of course, connecting components should have taken much less time, but that's a second or two single-threaded using something like union find. But we're fine with this, roughly. So maybe I'm inclined actually to wind down and let you folks go at this point. What I might do though is just show you in bidirectional Dijkstra the sorts of changes that we want to make, rather than actually go and screw around with differential and PR something at it. We'll just take a peek at bidirectional Dijkstra. It's not going to be too surprising. We are going to take in a bunch of edges and some goals. So these are the directed edges, source test. These are the directed goals of origin and target or something like that. And then we're going to iteratively go through and do some things. Now these are called forward and reverse. They're not what you think. These are forward and reverse bits of reachability. So who can we reach in the forward direction, from which locations, and at what distance. And similarly for the reverse. And where we actually use edges is down here. We join with edges. This would be in the forward direction. And down here, we join with edges having swung the edges around. That would be in the reverse direction. So if we had a forward edges and reverse edges, we would just throw them in here with a join core and join core. So forward, reverse. And the only thing that would be slightly annoying is that we would have to commit in the interface to bidirectional Dijkstra to an implementor of a trace type. we could do that. I don't want to sit through that compilation again and the 5 minutes of PageRank crap again. But I think, unless I've screwed this up terribly, I think you've probably gotten a sense for if someone were to show up with arrangements, these forward edges, reverse edges arrangements, ways that you can use them in your data flows at moments where you would otherwise be joining raw collections, and internal to join map would be building arrangements. You could just turn on the computation with existing arrangements of data. And interestingly, because this is the only place that we use edges, right? Building the data flow takes about no time, right? So building it and loading it with our edges. Imagine, if you will, that goals is initially empty. Building this and getting it ready to respond to changes to goals takes approximately no time. These are the single-digit milliseconds that we were seeing in our reachability examples. Right, so when we look at the gap between these two things, what we didn't even report was the time to build the data flow graph. So this is 140 milliseconds. To find the 100,000 neighbors, that's like non-trivial compute going on there. And but it takes very little time to actually put together the data flow for the neighborhood computation. Same would also be true for bidirectional Dijkstra. Very cheap to put the data flow together, and then the goal, looking for the goals is going to take some amount of time that depends on how much work we actually have to do. So there's no magic there. Like if we have to explore the entire graph, too bad. Yeah, we got to explore the entire graph. That's going to take a while. If there's an edge from the goal, from the origin to its goal, great. We'll be done in that single-digit millisecond, basically. So okay, so I think I'm just going to wind down there. I'll push this code at the repo. And I'm gonna stop there. Hopefully that learned us a little bit about how to write these things. Depending on time and whether it's really hot here at the moment, we might do some more things. We could make this be a bit. I think I'm really tempted to try to figure out, just for my own personal benefit, is how we can write these computations, literally the computations, so that we don't have to recompile nearly so much. That if we stopped editing PageRank, it stops recompiling PageRank each time. And I think we'll probably need to figure out how to remove the genericity here of G and use a more specific scope that we know about. And we will be able to see if the generic lifetime parameter hoses us on compilation and forces us to recompile everything, or if Rust is good to us and we can stop that madness. But, okay, we're going to wind down then. It's been a pleasure. Cheers and all that.